You just heard a custom asymmetrical clipping overdrive algorithm running on this custom bit of hardware, which is a digital guitar effects processing platform, which we've seen in a number of previous videos on this channel. In this video, I'd like to show you how you can implement your own overdrive algorithm for guitar or whatever musical effects you'd like to do, how it works, looking at time and frequency domain performance, doing some tests, and of course playing some guitar through it. We'll be mapping a couple of controls, including filter cutoff frequencies and the amount of distortion and overdrive, as well as the characteristics of the distortion to some of these potentiometers, and I'll guide you throughout the whole process. Flipping this guitar pedal over, we can actually see the core of this pedal, which is a main DSP PCB and actually a control PCB with the potentiometers below to make sure the mechanics work out. This particular PCB contains an STM32 which is a pretty beefy microcontroller which we're using for all of our digital signal processing. This interfaces to a Cirrus Logic codec via I2S, which in this case for this pedal I'm just using a single mono input and a single mono output, and all of these filter sections, these analog filter sections, are tailored for guitar. Pretty much all of the processing is done on this STM32 microcontroller, and I'll link some DSP and hardware design playlists below so you can make your own boards like this and see how the codec is set up, how the digital processing platform is running. In this video, we will be only focusing on the overdrive algorithm itself. Connections to the potentiometers are done via ADCs contained within the STM32 and these are connected via ribbon cable to the top PCB, which just has potentiometers on it. And I'm programming the STM32 via the serial wire debug connection using this very nifty tag connect header and an ST link. Before you continue with this video, I'd strongly suggest checking out video number 117 on this channel, which goes over the basics of DSP overdrive algorithms, in particular symmetrical soft clipping. This will also go into detail on aliasing distortion, what we do against that, and also give you an overview of the whole process. Of course, this is very similar to this video, although we are looking at a slightly different algorithm, but this serves as a good prerequisite and goes into a bit more detail than this video. Again, the link will be in the description box below. A huge thank you to JLCPCB for sponsoring this video. I had these digital guitar effect PCBs manufactured and assembled by JLCPCB, and they did an absolutely fantastic job. JLCPCB provides easy, affordable, and reliable PCB and PCBA solutions, which really empowers electronics engineers to develop projects efficiently and quickly. JLCPCB is super easy to use. We simply have to click on Instant Quote, add our Gerber files if we just want PCBs, or if we want assembly as well, we upload our Gerber files as well as bill of materials and pick and place files. Their pricing is incredible due to large-scale production, which reduces their and our costs. We can get 8-layer PCBs, for example, with 50 by 50 millimeters in dimensions for only $2. I've had a super good experience with JLCPCB. I can get my PCBs fully assembled back in about a week's time, which is amazing. Not only is their lead time super fast, but their quality is top notch as well. So I'd highly suggest you check them out. Links will be in the description box below and on my GitHub page as well. If you go to github.com/PMS67, I do have quite a lot of open source hardware available, including manufacturing files, which are specifically tailored to JLCPCB. So I'd strongly suggest you check those out. As we saw in the previous video, number 117 on symmetrical soft clipping, we start our overdrive endeavors based typically on the analog domain. In the analog domain, there are many different circuits available. They've been reverse engineered from guitar effects pedals, from amplifiers, if that's transistor or tube or valve based, and there are many different types of clipping methods that we can then use and emulate in our digital systems, be that overdrive and distortion and types thereof. There might be soft clipping, hard clipping, we can do valve and tube emulation, we can do fuzzes and much, much more. But broadly, the principles behind overdrive and distortion are very, very similar. If we look at a typical tube screamer schematic, which is one of the most popular overdrive pedals for guitar, all we have is an input buffer, some sort of non-linearity. In the analog case, this might be done with transistors or diodes to clip parts of the analog waveform. We have some filtering, that might be equalization, tone shaping, where we cut highs, boost lows, or whatever you want to do. You might have a volume control and an output buffer. Now, if you compare all of these analog overdrives, you'll pretty much find most of these elements, if not all of these elements, across them. What we can change is the type of clipping, input-output buffers, filtering, and much, much more. So it's a very, very creative area, and much so also in the digital domain, where it's quite easy with just a few lines of code, we can change the characteristics and the sound of our overdrive. But typically, we will start with some sort of analog prototype. In this video, we will be looking at asymmetrical clipping. Asymmetrical clipping might be based on something like a particular type of valve or tube, for example, a triode, which produces different types of harmonics when it's overdriven, when we have a large signal amplitude apparent at the input, and we'd like to model that in the digital domain, in the discrete time domain, because valves typically require high voltage, they're fragile, they're heavy. We can emulate, at least to a certain extent, that in digital software quite easily. Additionally, asymmetrical clipping might be used to emulate the effects of a fuzz circuit. For instance, the schematic shown in the bottom left is a simplified analog circuit for a fuzz face, which Jimi Hendrix used or made popular. We want to model this circuit, or at least the asymmetrical clipping part of that, and we can do that by modeling it using a simple static nonlinearity, and we can see that on the top right. Now, the equation initially might seem a bit complicated, but actually there's not much to it. We have x, which is our input, f of x, which is our output, q is some constant we can choose, and dist, or d we'll call it, is also just some constant we choose. Dist is the amount of distortion, and q is the shape of our asymmetrical clipping. For certain values of q and d, in this case this might be q equals minus 0.2 and d equals 8, we get this static characteristic, this transfer function, as shown in the graph. Our input axis x and output axis y. So for positive going signals, we have this fairly linear characteristic, but for negative going signals, we are compressing the signal quite down and we're distorting it quite significantly, and therefore we will get an asymmetrical clipping, depending on our input waveform. We can then play with our distortion and Q parameters to change the shape, and that then changes the tone. But our asymmetrical clipping, it will have a few different components around it, has at the center this asymmetrical clipping nonlinearity, which is a static conversion. I'd also strongly suggest playing around with this static nonlinearity, playing around with the parameters Q and D. And you can do that using a graphing calculator. My preferred one is Desmos, which is free at desmos.com/calculator. So I've popped in this asymmetrical clipping static nonlinearity, and I've made the parameters Q and D variable with these sliders. So again, Q controls the symmetry of this clipping, and D is the amount of distortion. Q can't be 0 and Q should be negative, is one constraint, and typically D is a positive number. Now for a Q of minus 0.2 and D equals 10, we can see this asymmetrical clipping waveform. So for the positive side, we have a fairly linear slope, and for a negative input, we have this fairly hard clipped asymmetrical nonlinear slope. As we increase D, or the amount of distortion, we can see particularly the knee of the asymmetrical part gets much harder, and we have maximum clipping already at an input amplitude of minus 0.2. As we reduce D, we can see that knee gets softer. We don't get quite as aggressive clipping in the negative side. Now if we make Q more negative, we can see our characteristic actually gets more symmetrical or less asymmetric. For a value of Q of about minus 1.5, we pretty much have a linear mapping, meaning actually we're not clipping terribly much. The clipping will probably just be an occurrence of how much gain, how much amplification we apply, and the bounds of our hardware and our dynamic range. So Q is a control we can definitely play with. It doesn't have to be minus 0.2. It could be somewhere between 0 and minus 1.5. And that also changes the characteristics of our overdrive and our distortion. And we can, of course, play around with this factor D, which changes the knee of our asymmetrical clipping. If we then feed a sinusoidal signal into this asymmetrical clipper without any other effects or filters applied, we can see this on the left-hand side for a low amplitude input signal, on the right-hand side for a higher amplitude input signal. Again, because of the static nonlinearity, we can see the negative part of our waveform is clipped harder and earlier than the positive part. So what might be a 1 kHz sine wave now looks significantly distorted, but it's not a symmetrical distortion. In the frequency domain, again passing in low amplitude input signals and increasing the amplitude, because of the nonlinearities, we will get different spectra at the output. So the f of t, or the frequency domain content, is of course dependent on the input amplitude, because this is nonlinear. For this output signal we see in the top left, where we have not terribly much distortion applied, not terribly much non-linearities, we can see the fundamental in the spectra on the right-hand side. So the f of t at 1 kHz, we have our fundamental, but we do see a second harmonic at 2 kHz creeping in, even though the output signal looks still fairly sinusoidal. This is very similar to the behavior of a triode valve or triode tube. As we increase the input signal, the output signal, as shown in the bottom left of this image, is heavily distorted. Very, very asymmetrical, very distorted. And then on the bottom right-hand side, we see the corresponding FFT, the frequency spectrum, where now we have the fundamental at 1 kHz, but we also have 2, 3, 4, 5, 6, and so on. All the odd and even harmonics are in the frequency content of this output waveform. If we compare that back to video number 117, the symmetrical soft clipping had the fundamental and only odd harmonics, so we expect a different sound of this as well, and different use cases. I keep referring back to video number 117, but it is important that if you haven't seen this before that you do watch this, because I go into detail on some of these blocks in this block diagram. Our digital overdrive is very flexible, so it does not have to follow this structure which I'm showing here. We can move filters around, we can add filters, we can do parallel processing, we can mix symmetrical with asymmetrical clipping. We really can do very much to create your own unique sound. What is important, however, is that before we perform our static non-linearity, is that we add in an anti-aliasing filter. Because we're adding a non-linearity, this will generate new frequency content, and that might then, because we're in the discrete time digital domain, alias back down into our baseband and give us aliasing distortion, which, to be honest, doesn't sound particularly nice compared to the actual distortion we're trying to achieve. So typically, what is fixed is that you have an anti-aliasing filter, which reduces the bandwidth of our input signal before we feed that into our static nonlinearity. Now, around that, you can add in variable blocks. This could be equalizers, you could be adjusting the gains, you could be adjusting the cues, cutoff frequencies, and much, much more. But typically, you might have some sort of equalizers or filters before your static nonlinearity, before your anti-aliasing filter, for example, low and high pass filters. And at the end, you might want to add some more high and low pass filters to remove some of the nasty, very high frequency harmonic content. You might want to remove some of the low frequency content to avoid muddiness in your overdrive signal and generally shape the sound. Our overdrive will roughly follow this block diagram where we have some equalizers before, we have some anti-aliasing filter, and we have a static nonlinearity, which we just saw from the asymmetrical clipping, and then an equalizer at the end. Now, we might move this around, and I'd suggest you check this out and try this out for yourself to see what you like the sound of. But again, in essence, it's a simple cascade of different blocks, and we can move those around within reason. Now let's move over to STM32 Cube IDE and continue our project where we're programming the STM32H7 to do this digital overdrive. Again, I'd strongly suggest checking out video number 117. This will go into detail on aliasing distortion, how to design the anti-aliasing filter, and in our case, this will be an FIR filter with a specific cutoff frequency chosen for our particular clipping algorithm. For instance, for quadratic nonlinearity, we might want a cutoff frequency at a quarter of our sampling rate. For something like asymmetrical clipping, where we have an exponential, we might want to decrease the signal bandwidth even further. So please check out that video and how to design this FIR filter. But also this will guide you through the main elements of the software implementation. In this video, I would like to just show you how to implement the asymmetrical clipping nonlinearity. Everything else is pretty much the same as this video number 117 in terms of software, which goes into detail. Now, in the software project, also from the previous video, we have our overdrive update function, which takes in our current input sample, which we retrieve through the ADCs from the codec. Right now, I've left in the FIR low-pass filter from the previous video, which has a cutoff frequency of fs/4. It might be worth playing around with decreasing that cutoff frequency to attenuate the effects even more of aliasing distortion. But all this is doing is running through an FIR low-pass filter, and I do also have videos on that on my channel. After the FIR low-pass filter, we have a variable first-order IIR high-pass filter. So I've mapped this IIR high-pass filter to a potentiometer on the PCB and on the guitar pedal, which we can then play around with. We can change the cutoff frequencies dynamically on the go, and this is why this is an IIR filter. Also, I like placing my high-pass filters before the distortion because that will remove some of the low-frequency content, which might otherwise sound pretty muddy if we don't do that before the distortion. Following this first-order IIR high-pass filter, I've commented out our previous overdrive, which is our symmetrical soft clipping, and I've added in my symmetrical clipping. Another control that I have on this PCB is the overdrive, or the amount of gain we can add. So this is just a simple constant I multiply with my input signal or whatever has just come out of that high pass filter. So we can adjust this constant, or rather than it's a variable, of course, with the potentiometer. So I'm pre-multiplying my input signal by a fixed amount. This could be 50, 100, 200, depending on how much distortion you want. Now we see our coefficients D and Q again coming up, and for D I've now just chosen 8, and Q I've actually also made variable and I've mapped that to another potentiometer on the PCB. Q in my case will go from just under 0, so negative 0.01 for instance, down to about -1, -1.2. And then that again changes the characteristics of this static nonlinearity. And all I'm doing here with this first term is computing part of this static nonlinearity. There's one part which doesn't change, unless we change Q, of course, which is this plus Q divided by 1 minus e to the D times Q term. So if you don't have a Q that changes, you can of course save that as a constant. But since we have to make sure also that X is not equal to Q, because then we get 1 minus e to the minus 0, where we get a 1 divided by 0 error. So we have to check this corner case that we don't have X is equal to Q. So therefore, after computing this pretty much constant part, I'm checking if the absolute value of X minus Q is above 0, or above some sort of threshold value, and I've just put an arbitrary small threshold here. But if X is not equal to Q, so that means X minus Q is greater than this threshold value, we can compute the left-hand side of this asymmetrical static nonlinearity, which is this X minus Q divided by 1 minus e to the minus D times X minus Q. And that's all I'm doing here. So I've already pre-computed the right-hand side term. If X is not equal to Q, we can compute the left-hand term and just add that to what we computed previously. So that's all I'm doing. I'm doing X minus Q divided by this whole term here. Copied straight from the nonlinearity, except of course that X I'm pre-multiplying with my pre-gain. After asymmetrical clipping, I've then added in a variable IRR low-pass filter, meaning I've mapped the cutoff frequency to one of the potentiometers on the PCB, and this low-pass filter is there to remove some of the high-frequency content after clipping. Some of these higher-order harmonics don't sound particularly pleasant, so we can roll them off, we can attenuate them with this low-pass filter. The output should be bounded between 1 and -1 anyway, but I'm just making sure that we have a clamp in place. And after that, I'm simply returning the latest sample from our overdrive algorithm. Then in my main processing loop, we've seen that in the previous video, I'm just looping through the current ADC samples collected via I2S and DMA from the codec, converting them from assigned 24-bit integers to normalized floats between -1 and +1, applying an output volume, so just multiplying by a number between 0 and 1, and calling my overdrive update function with my current input sample and then looping through that array. And that's all I'm doing. And I've mapped the various controls as we talked about to several potentiometers. So now let's upload this to the board, connect it to some test equipment and see what this looks like in the time and frequency domain before we play some guitar through this. I've now uploaded the firmware to this guitar effect pedal. Our overdrive algorithm is running, and we like to first of all test that before playing any guitar through it. We just want to see this in the time and the frequency domain. So to do that, I'm using an Analog Discovery Pro by Digilent, which is a USB-based WaveGen and oscilloscope. And I've selected WaveGen 1, generating a sine wave, frequency 1 kHz with an amplitude of 100 millivolts. That is connected to the input of this guitar effects pedal. I'm running at only 100 millivolts because of course we have a lot of amplification, we have a lot of gain in our guitar pedal system. The output of our guitar effects pedal is then connected to channel 1 of the scope, and it's currently running our algorithm. Right now, I have some amount of distortion applied. I've set the output volume to a certain amount. I can twiddle that around here. But I also have my Q set up, as we can see on the right-hand side. So the Q is fairly negative, meaning we get a fairly linear response. There isn't terribly much clipping going on at the moment, at least not that we can see with the naked eye. The positive and negative parts of this waveform look fairly sinusoidal. But as I now increase Q, so make it less negative or make it more positive, we can see in the static nonlinearity, we should get this asymmetrical clipping on the negative part of the waveform far earlier. So now let me adjust my Q on the pedal and see what happens. And that's exactly what we're getting. The positive half of the waveform seems pretty much unaffected, and that makes sense with what we're seeing on the static nonlinearity, but the negative part of the waveform is cut off, it's clipped at a certain point, and that depends on how much Q we change. So if I make Q more and more positive, as expected, we get much more aggressive distortion or nonlinearities forming on the negative part of the sinusoidal or previously sinusoidal waveform. If I go Q in the opposite direction, we recover and we get less aggressive clipping. So that's how we can play with this Q factor to change the effect of our clipping. Other than the Q, of course, we can change our amount of distortion. So if I reduce the amount of distortion below a certain point, we are getting pretty much no distortion at all. But as I increase my overdrive, my pre-gain, you can see now also the top part of my waveform is clipping as well as the negative part, and it looks far more symmetrical. If we look at that on an FFT, I can select my FFT. I'll increase my time base to get more resolution on the FFT. We can see all of these harmonics. So we have the fundamental at 1 kilohertz. We've got even at 2, odd at 3, and so on. If I decrease the amount of distortion, reducing my pre-gain, we can see those harmonics are dropping away as well until we have something like a sinusoidal wave. But as I increase my distortion again, those harmonics will come out. As I change my Q factor, of course, that will change the amount of harmonics. So as I make it more symmetrical, less clipped, we get less harmonic distortion. As I make it more asymmetrical, more clipped, we get more of this harmonic distortion. So this is how we can play around and see in the time and frequency domain what happens. We of course also have our high and low pass filters. So my high pass filter is pretty much maxed out currently, but as I decrease the cutoff frequency, we'll see the amplitude of these harmonics will drop as well because we're removing the high frequency content. We can of course see that a bit better in the time domain as well. So this is with maximum cutoff frequency of the high pass filter. It's not terribly doing very much, but as I decrease the cutoff frequency, we will start smoothing out those edges. It's still pretty distorted. As you can see, it's not terribly sinusoidal, but it's definitely less distorted than before. And that's because we are attenuating these higher frequency contents in the output waveform using our high pass filter. But of course, we can also change the low pass filter as well. But for this, we won't see terribly much of an effect. But I think this is quite cool to play around with to see if all this asymmetrical clipping makes sense, if this is actually what we're seeing in our output waveforms and our FFTs. But now let's move over to playing some guitar through this. I've got my guitar plugged into the guitar effects pedal, which in turn, its output is running into my audio interface connected to my PC. On my PC, I'm running Guitar Rig 7 by Native Instruments, and all I have engaged there is a matched cabinet Pro, which is a Lead 800 cabinet. I'm not running amplifier simulation, running no pedal emulations, just a tiny bit of room reverb, so this is what it sounds with the pedal disengaged. So a pretty standard, boring, clean sound. Now let's engage the guitar effects pedal. I've got my Q setting all the way clockwise, my gain is pretty much maxed out, and my low and high at some fairly mid-ish random settings, and my volume to match. So now let's engage. So it sounds pretty cool, I think, for such a simple algorithm. Let me reduce the gain. So the harder I play, the more distorted it gets, of course. I can play around with the EQs. And of course I can play around with the Q setting. So moving it between this more symmetrical and harder clipped asymmetrical waveform. So you can really hear it changes the characteristics of the distortion quite a bit from this rather full sound to this bit more tinny sound. So it might be cool to play around, blend them in between a tiny bit. But such a simple algorithm, we can get quite a lot of different sounds out just by making some of these parameters variable. We can play with the filters, cutoff frequencies, and much, much more. So I think it's quite a cool, simple demonstration of what we can do with DSP. Thank you very much for watching this video. I hope it was useful, and I hope it showed you how easily you can create your own overdrive and distortion effects, be that for guitar or other instruments or for any other purpose. If you have any questions, please leave them in the comments below. If you like the video, please leave a like, and don't forget to subscribe to stay up to date with any latest embedded systems, hardware, PCB design, and DSP videos. Thanks again for watching, and I hope to see you in the next one. Bye-bye.